The purpose of this project is to apply fundamental engineering principles including load distribution, structural stability and material strength in designing and constructing a functional bridge model. It incorporates essential physics concepts such as force distribution, tension and compression and stability to ensure the effectiveness of the design. Through the construction of a small-scale beam bridge model, the project replicates the principle of full-scale bridges, demonstrating how real-world beam bridges efficiently manage loads and maintain structural integrity. The objectives of this project are to design and construct a bridge capable of withstanding a load of at least 5 kg. The bridge must be built within the specified dimensions of 50 cm x 50 cm x 50 cm, adhering to size constraints while ensuring structural efficiency. Additionally, the project involves analyzing the strength and stability of the bridge structure using the provided materials to evaluate its performance. These efforts emphasize teamwork, requiring collaborations to enhance problem solving, critical thinking, and engineering design skills throughout the construction project. Introduction. The bridge being built is a beam bridge, which is a simple structure consisting of a horizontal deck supported by vertical columns to distribute the load evenly. Beam bridges are widely used due to their straightforward design and effectiveness. For this project, the bridge is intended to carry minimum load of 5 kg, which simulates real-world weight challenges. This capacity will be achieved by strategically designing the structure and reinforcing it with multiple layers of materials. The primary material for this project is ice cream sticks, which are lightweight yet strong when layered and glued together. Glue or adhesive such as wood glue or hot glue will be used to bond the sticks securely. A cardboard or wooden base will serve as a stable foundation, ensuring the bridge remains construction and testing. For load testing, objects like bricks weighing up to 5 kg will be used. The tools required for this project include scissors or a craft knife to cut the ice cream sticks to precise length and shapes, as well as a ruler and measuring tape to ensure the bridge meets the required dimensions, including a 30 cm span and at least 5 cm width. Clamps can be used optionally to hold glued parts together while they dry for added stability. A pencil or marker will also be used for marking measurements and design guidelines on the materials. With the proper combination of materials and tools, this project aims to construct a functional and durable beam bridge capable of meeting the load requirements. Next, we are going to see our design sketches and diagrams of the bridge. Now, I am going to explain about rationale behind design choice. Our design choices are carefully made to ensure optimal load distribution, prioritizing safety margins, and achieving significant weight reduction. By using materials such as skewers and popsicle sticks, we have selected components that can reliably withstand applied loads without deformation or failure, ensuring durability and structural integrity. Additionally, we considered cost and availability as crucial factors in the design process. This approach allows us to create a balance between performance and affordability, making the design accessible and practical for real-world applications. The chosen materials and methods also provide flexibility, enabling adaptability to various design requirements without compromising efficiency or reliability. Overall, our rational design choice emphasize safety, affordability, and sustainability to meet project demands effectively.
I would like to talk about our bridge building with popsicle sticks, which is an exciting way to learn about engineering, physics, and design principles. Our main objective is to build the strongest, most efficient bridge that can hold the maximum weight with minimal materials. So, our key concepts are: first, the types of bridges. Our bridge is more to the truss bridge, which uses triangular units to distribute weight, offering a stronger design. Our first step to build the bridge was planning and design. We had to sketch out the bridge design before construction. Other than that, we also had used popsicle sticks and hot glue gun for materials and scissors for tools. Our main tips for success to hold more than 11 kgs of weight was using triangles in the design. Triangles are the strongest shape in construction, for your knowledge. We should also focus on clean, precise joints for better weight distribution, and test small sections of the bridge before final assembly to ensure strength. That's all from me. Thank you.
We had to go through a number of engineering principles to build this bridge. Firstly is the tension and compression. Tension occurs when materials are pulled apart, like at the bottom of the bridge. Compression happens when materials are pushed together, like at the top of the bridge. Secondly is the load distribution. Bridges must distribute the weight evenly across the structure to prevent it from collapsing. Lastly is the efficiency of the materials. The use of popsicle sticks will balance the strength and the weight. We also had to consider a lot of designing aspects to build the best bridge we can. First up is the weight to strength ratio. The bridge should be as light as possible while being able to withstand heavy weight. Secondly, the joint strength. We had to glue and align the structure correctly. Lastly is the symmetry and balance of the popsicle bridge. A well-balanced design will make sure that the weight is evenly spread through all the alignments.
Load testing a beam bridge is basically assessing its strength and structural integrity. This process is done by applying load and weight on it. Then the beam bridge is also tested by gradually increasing the load on it. The beam bridge made by my group mates out of popsicle sticks is able to withstand up to 11 kg load. Since it has enough vertical and horizontal support, we did not encounter any sign of bending, cracking, or joint failure throughout our observation. To sum up, I would confidently say that the beam bridge constructed by my group mates and I ensures a consistent design that mimics real-world beam bridge. And here's the glimpse of the testing process. Thank you.
During the construction of the ice cream stick bridge, several valuable insights were gained, particularly in terms of structural integrity and design considerations. A major success was the stability provided by the main beams and vertical supports, which helped distribute the load effectively across the bridge. This was key to ensuring that the bridge could bear weight without collapsing. The precise placement of vertical supports and the careful gluing of the deck provided the necessary strength for the structure to hold up during testing. However, there were also challenges faced through the process. One of the main issues was achieving perfect alignment of the beam and supports, which occasionally caused instability during the initial stage. In some cases, the glue didn't bond as quickly as expected, and this required more time for the glue to set, slowing down progress. Additionally, finding the right balance between the weight of the materials and the bridge's ability to bear load was a challenge, especially during the testing phase when some parts of the bridge began to bend under pressure. Modifications were made based on the result from testing. For instance, additional cross braces were added to the main beams to increase stability after the initial test showed slight sagging. Also, more vertical supports were added in areas where the load seemed to concentrate the most, which help reduce the risk of failure in those parts of bridge. Looking ahead, there are several areas for improvement in future designs. A more uniform distribution of weight across the deck could be achieved by adding more cross beams and supports. In addition, using a stronger adhesive or experimenting with different materials could help reduce the risk of bond failure. Future designs could also benefit from more precise cutting and alignment, ensuring that each piece of more securely and is better positioned to withstand load stress. Overall, the project provides a deeper understanding of engineering principles and the importance of careful planning and testing in the construction process. In conclusion, the Popsicle Stick Bridge competition serves as a remarkable platform for students to cultivate essential skills such as critical thinking, innovative design, and practical engineering principles. Beyond being a simple project, it introduced participants to the complexities of bridge construction in a hands-on and engaging manner, emphasizing real-world applications. This activity inspires creativity and allows students to experiment with different structure materials and strategies to achieve optimal strength and efficiency in their design. In essence, the competition transformed learning into an exciting experience, motivating students to explore engineering concepts in an interactive and enjoyable way. It instills confidence, nurtures curiosity, and prepare participants for future endeavors in STEM field while also encouraging a sense of accomplishment and camaraderie.